physicsinfo.co.uk. Another in the series of Physics GCSE tutorials. Separate sciences. Radioactivity, Topic 6. We're going to start this video by looking at the history of the atom. The original name atomos comes from the ancient Greek for uncuttable. And then J.J. Thomson found that there were electrons, so it was even smaller. Rutherford decided that the nucleus was very compact. And then people like Bohr went on to describe electron shells.
But back in the 19th century, scientists thought that everything on Earth was made of just over 80 elements. These elements were famously arranged in a periodic table by Dmitri Mendeleev. At the time, it was thought that elements were made of indivisible spheres called atoms. But each of the elements behaved in a different way. Did that mean that there were 80 different kinds of atom? And if so, what made them different? Were they different shapes or sizes? Or maybe the atoms were divisible. Maybe they were built of even smaller objects.
Everything is made of atoms. But what are atoms made of? Scientists used to believe that atoms were solid particles, like tiny snooker balls. They thought atoms couldn't be split apart. This idea was changed in 1897 by J.J. Thomson. He was investigating the properties of cathode rays using this piece of equipment, an empty glass tube. Here's a modern version of Thomson's apparatus, an evacuated tube containing an anode and a cathode. Heat the cathode and it produces a beam of cathode rays. The beam cuts across a fluorescent screen. Scientists knew that a magnetic field could deflect the path of a cathode ray beam. Turn the magnet round and the beam is deflected in the other direction. Thomson measured the size of this deflection. He worked out that cathode rays were made of tiny particles, hundreds of times smaller than an atom. Thomson was also the first to deflect these beams with an electric field. The screen sits between two horizontal charged plates. An electric field between the plates deflects the path of the beam upwards. The positive plate attracts these cathode rays. The negative plate repels. Reverse the connections so that the polarity swaps over and the beam is deflected in the opposite direction. Again, attracted to the positive and repelled by the negative. From this, Thomson concluded that cathode rays must be made of negatively charged lightweight particles.
Thomson had discovered the first subatomic particle, the electron. Thomson had discovered that the atom is not the fundamental building block of matter. There are smaller objects inside. So atoms could no longer be thought of as hard, indivisible spheres. But how do the electrons fit inside the atom? Thomson suggested that the atom was something like this muffin, with the negatively charged electrons embedded in a positive body.
This was the so-called plum pudding model, where negative electrons are embedded in a mass of positive charge, the radius of each atom being about 10 to the minus 10 meters.
The mystery of how the electrons fitted inside the atom was eventually solved here in Manchester, in this building in 1911, by Ernest Rutherford. Rutherford was, in my opinion, one of the first proper particle physicists because he used beams of particles as projectiles to explore the structure of matter. Now, of course, in Rutherford's day, there was no such thing as a particle accelerator. So he used the decay of radioactive elements to produce his beams of particles. Rutherford asked two of his students, Hans Geiger and Ernest Marsden, to fire some alpha particles at a piece of thin gold foil and see what happened. So imagine these tennis balls are the alpha particles. Now, if the atom were, as Thomson had suggested, a kind of amorphous blob, then you'd expect the alpha particles to pass right through. And that's indeed what happened to most of them. But to their surprise, they found that around 1 in 8,000 bounced right back.
This is an animation of Rutherford's experiment where he fired alpha particles at gold foil. Now, we would call that gold leaf. Now, Thomson's model was of a positive sphere with electrons embedded, so it was expected that the alpha particles would pass straight through. He described it as firing a cannonball at tissue paper. The results were somewhat different than expected. Most alpha particles did indeed pass straight through. Some were deflected by small angles, but some were deflected by large angles, and even a few bounced all the way back. The cannonball had been sent back by the tissue paper.
After 2 years of puzzling over the meaning of these results, Rutherford realised that in order for the alpha particles to bounce back, they must hit something small and dense. So his new model of the atom was a bit like the solar system, with all the mass concentrated at the centre and the electrons orbiting like planets around the sun.
Today, we know that this picture isn't quite correct. Quantum mechanics tells us that we can't know precisely where the electrons are.
Using the animation again, Rutherford proposed that because most of the alpha particles pass straight through, that the atom was largely empty space. With very few deflections, the nucleus had to be small and dense. And because some of the alpha particles bounced back, the nucleus had to have a positive charge to reflect the positive alpha particles. We'll look at electrons and electron shells a bit later.
Rutherford had come to the astonishing conclusion that most of the atom, and therefore most of what we think of as ordinary matter, is in fact empty space. So if this apple were the atomic nucleus, the electrons would be a kilometre away.
After discovering the nucleus, Rutherford continued doing experiments, firing particles at different targets to delve into the structure of the nucleus itself.
Thomson had discovered the electron, and Rutherford had shown that atoms have a small, dense, positively charged nucleus. Next, they needed to find out what, if anything, made up this nucleus.
Following Thomson and Rutherford, scientists have now discovered lots of particles inside the atom. You need to know about 3. The proton, the neutron, and the electron. A proton has a positive charge. A neutron has no charge. An electron has a negative charge. The nucleus of most atoms is made up of protons and neutrons. The only exception is the hydrogen nucleus. It contains just 1 proton. Each nucleus is tiny compared to the rest of the atom, which is almost all empty space. The only things there are electrons orbiting the nucleus at very high speed.
Just to clear up any confusion between beta minus and positrons, when you get a beta minus, a neutron turns into a proton. When you get a positron, a proton turns into a neutron. In summary, protons have a charge of +1 and a mass of 1 atomic mass unit. Neutrons a charge of 0 and a mass of 1. Electrons a charge of -1 and 1/2000th of an atomic mass unit, and the positron, which is a positive electron, a charge of +1 and a mass of 1/2000 of an atomic mass unit.
The periodic table is the most popular chemical pin-up in the world. In every science lab, you'll find the elements set out in exactly the same order. The layout isn't alphabetical, but it isn't random either. Every element in the periodic table is arranged in order of increasing atomic number. To understand atomic number, you need to look into the heart of an atom. Take hydrogen, the first element in the table. Orbiting around the outside of each hydrogen atom is one electron. And in the nucleus is one proton. Like all protons, it has a positive charge. Every hydrogen atom is the same. The atomic number is simply the number of protons in the nucleus. A hydrogen atom has one proton, so hydrogen's atomic number is 1. Atomic number is usually written to the bottom left of the element symbol. So what about the next element in the table, helium? What's its atomic number? Helium has 2 electrons orbiting around the outside. In the nucleus there are 2 protons and 2 neutrons. The atomic number is simply the number of protons. So the atomic number of helium is 2. The next element along the periodic table is lithium. Orbiting round each lithium atom are 3 electrons. In the nucleus there are 3 protons and 4 neutrons. So what's the atomic number of lithium? The number of protons is 3, which means that the atomic number is also 3. As you move across a row from left to right, the number of protons increases by 1, so the atomic number also increases by 1. An element's atomic number determines its position in the table. Another number you need to understand is called the mass number. The mass number at the top position is usually a bigger number than the atomic number at the bottom. Move along a row, the atomic number increases by a steady unit of 1 each time, but the mass number changes by irregular amounts. To understand mass number, once again, we need to look inside an atom's nucleus. Mass number is the number of protons plus the number of neutrons. Hydrogen has just 1 proton in its nucleus and no neutrons. Its atomic number is 1, and its mass number is also 1. So what about helium? It has 2 protons and 2 neutrons. 2 plus 2 is 4, so the mass number of this helium atom is 4. Next, look inside a lithium nucleus. Can you work out its mass number? 3 protons and 4 neutrons mean the mass number is 7. Each element has a unique atomic number. It's the number of protons in an atom's nucleus. It also tells us the number of electrons orbiting an atom's nucleus.
It was the Danish scientist Niels Bohr who came up with a mathematical model for electrons orbiting the nucleus. He proposed that electrons existed in fixed shells of fixed energy and of limited capacity.
To show how electrons orbit the nucleus, we're using a model. Here, electrons are represented by roller skaters. The orbits occupied by the electrons are circles. The nucleus is the square in the middle. Each atom has the same number of electrons as protons, so if the atomic number is 12, there are 12 protons and 12 electrons. But where are these found? Electrons don't move at random. They circle the nucleus in orbits called shells. Each shell holds a fixed number of electrons. To take a closer look at how these shells are filled, we're going to start with the 3 simplest elements: hydrogen, helium and lithium. Hydrogen has an atomic number of 1. It has 1 proton and so 1 electron. This single electron goes into the first shell nearest to the nucleus. Next, helium. Its atomic number is 2, so it has 2 electrons. They both go into the first shell. But what about lithium, which has 3 electrons? 2 is the maximum number for the first shell, so the third electron has to go into a second shell. There's a limit to how many electrons each shell can hold. The first shell holds a maximum of 2 electrons. The second shell holds a maximum of 8 electrons. The third shell can also take 8 electrons.
This is a representation of the neon gas we were talking about earlier. The model of the atom keeps changing and improving, but we've seen that electrons in an atom exist in shells of fixed energy. So let's explain why neon gas gives off an orange glow when a current is passed through. Electromagnetic radiation, in this case green light, can provide exactly the correct amount of energy for an electron to jump energy bands, energy levels. This electron will stay there for a short while before falling to a lower energy band, in this case emitting orange light. Electrons will absorb light of very specific frequencies, giving an absorption spectra, and then they'll fall down a shell level and give off light of another specific frequency. By definition, all atoms of the same element contain the same number of protons. That's the atomic number. Isotopes of an element have the same number of protons, but the number of neutrons, and hence the mass number, varies. Isotopes of an element are atoms with the same number of protons but different numbers of neutrons. As a result, they have different masses. Thomson and Aston investigated neon and found 2 isotopes, one with 10 protons, 10 electrons and 10 neutrons, the other with 10 protons, 10 electrons and 12 neutrons. These are the 2 isotopes, neon 20 and neon 22. The total number of protons and neutrons gives you the mass number. Actual mass is a little bit different because of the electrons, but they're so small we tend not to count them.
A typical atom, this is an atom of the element carbon, has 3 types of particles: protons, neutrons, and electrons. The protons have a positive charge, the electrons have a negative charge, and the neutrons have no charge. There are the same number of protons as electrons, so the atom overall is uncharged. Atoms of different elements have different atomic numbers. The atomic number is simply the number of protons. For carbon, it's 6. Add together the number of protons and neutrons, and you have the mass number. 6 plus 6 is 12, so this is an atom of carbon 12. What is this? 6 protons, 8 neutrons, 6 plus 8 equals 14. Atoms of the same element with different mass numbers are called isotopes. This is carbon-14.
Moving on to radioactivity, or we should more properly call it ionising radiation. Unstable nuclei will decay randomly in a number of possible different ways to try and become more stable. They can emit particles from the nucleus, such as alpha or beta particles, or they can give off electromagnetic radiation in the form of gamma rays. When a nucleus is big and it contains lots of protons and neutrons, it tends to be unstable and will kick out particles to find a better stability. Alpha decay is when 2 protons and 2 neutrons leave the nucleus, leaving a remaining smaller atom plus the helium nucleus.
Some elements have many more neutrons than protons. These are the elements with large atomic numbers. For example, uranium-238 has 92 protons and 146 neutrons. The imbalance makes the nucleus unstable. It emits a particle which consists of 2 protons and 2 neutrons. It is actually a nucleus of a helium atom. This type of emission is called alpha radiation. Because the particles are large, they collide frequently with atoms in the paper. They lose their energy and stop quite quickly. As the uranium-238 emits the particle, it becomes a new element, thorium-234, with different mass and atomic numbers. The helium atom completes the equation.
When a radioactive atom emits alpha radiation, it loses an alpha particle from its nucleus. Each alpha particle is made of 2 protons and 2 neutrons. Alpha radiation consists of positively charged particles.
Beta decay, a neutron splits into a proton and an electron, which is ejected from the nucleus. The proton number goes up.
Emissions from elements with much smaller atomic numbers are different. In this process, a neutron changes into a proton and an electron is emitted. This is called beta radiation. The beta particle is very small, so is much less likely to collide with other atoms and can therefore penetrate much further. In beta emission, the mass number stays the same, but the atomic number increases by 1. The carbon-14 has decayed to become nitrogen-14.
When beta radiation is emitted, a neutron in the nucleus splits into a proton and an electron. The electron shoots out of the nucleus at high speed. Beta radiation is a stream of high-energy electrons. This electric arc is also a stream of electrons. See what happens when a magnet is placed nearby. Because electrons are charged, their path can be deflected by a magnetic field. The same would happen with beta radiation.
Comparing the 2 types of emission, the alpha particle is much larger than the beta particle. Alpha is stopped easily, beta travels further.
Finally, gamma decay occurs when the nucleus rearranges. The protons and neutrons find a more stable configuration. The atomic number and the mass number don't change.
Often when an atom loses alpha or beta particles, it's still unstable. It can lose more energy in the form of electromagnetic radiation. This is gamma radiation. Because gamma radiation doesn't involve the emission of a particle, it has much greater penetrating power than either alpha or beta.
Unlike alpha and beta, gamma radiation is an emission of high-energy rays. It isn't made of charged particles, so won't be affected by a magnetic field.
Ionising radiation can be detected by photographic paper, as with the Rutherford experiment, or the Geiger-Müller tube. Units are counts per second or becquerels. The unit of activity is the becquerel. Geiger counters can be used to show that radiation is everywhere, and this is called background radiation and can come from rocks, space, food, hospitals, even from us.
This sign is known all over the world as the hazard symbol for radioactivity. The radiation emitted from a radioactive source is invisible, but a Geiger-Müller tube attached to a counter can detect its presence. The greater the number of clicks, the higher the level of radiation. Remove the radioactive source and the count falls, but it doesn't drop to zero. Wherever you are, there's always a low level of so-called background radiation. Whether you're out in the street, in the middle of the countryside, even inside your home, a Geiger counter continues to detect low levels of background radiation. That's because all sorts of materials are naturally radioactive. This rock contains the element uranium. Even this wall tile is emitting radiation. And just listen to this old watch. The luminous paint on its hands contains the radioactive element radium. This is the amount of potassium chloride in an average human being. A small percentage is radioactive. Cosmic rays reaching us from outer space also contribute to the general level of background radiation. The cloud chamber also makes the effect of some nuclear radiation visible. The chamber contains air saturated with alcohol vapor. The metal disc in the middle is a radioactive alpha source. As the radiation shoots through the alcohol, it leaves behind a vapor trail. That's because nuclear radiation ionizes air. When the radiation collides with atoms in the air, it dislodges electrons. These air particles become positively charged ions. As the radiation passes through the air in the chamber, it leaves a trail of positive ions behind. The surrounding alcohol molecules condense on these ions to form a trail of tiny droplets. In this way, the path taken by the radiation becomes visible. Although nothing appears to be happening, all these substances are emitting nuclear radiation. It's invisible, but an easy way of detecting it is to use a Geiger-Müller tube attached to a counter.
Now just a brief look at how the Geiger-Müller counter works. Ionizing radiation passes through a mica window, which allows the radiation through but prevents the argon gas at low pressure from escaping. Radiation hits the gas and produces ions, which get attracted to the anode and the cathode, producing a small electrical signal.
There are 3 different types of nuclear radiation: alpha, beta, and gamma.
Let's look at the dangers of the different types of ionizing radiation. The production of ions inside a cell can cause mutations. The best protection is shielding, distance, and time. The alpha particle is a helium nucleus with 2 protons and 2 neutrons. It has a 2+ charge and is highly ionizing. It is not penetrating and will travel only a few centimeters in air. Hence, the risk is low.
This is an alpha source. At this distance, The count rate is about 500 per second. Place a thick sheet of paper in its path and all the alpha radiation is absorbed.
Beta-minus particles are fast-moving electrons with a charge of -1 that are emitted from the unstable nucleus when a neutron turns into a proton. They have a range of energies and can penetrate up to a few centimetres into the body. They are dangerous.
This is a beta source. It emits only beta radiation. The count rate is over 600 per second. Place a piece of paper in its path and the count rate falls only slightly. Some of the beta radiation has stopped, but most travels through. Replace the paper with a denser material and the count rate drops much further. Beta radiation is absorbed by a thin aluminium sheet.
Gamma rays, unlike alpha and beta, are not particles. They are electromagnetic waves. Highly penetrating, they are not very ionising. In small numbers, their risks are low.
Cesium-137 is a source of gamma radiation. At this distance, the count rate is about 50 per second. Place a piece of paper in its way and nothing happens. A thin sheet of aluminium also has no effect. Gamma radiation is very penetrating. Several pieces of lead are needed to absorb this high-energy radiation.
To summarise, we have large alpha particles with a 2+ charge. We have positive electrons, positrons, and negative electrons, beta-minus, both with a tiny mass. And finally, gamma rays, which are electromagnetic radiation. And finally, radioactivity half-life. Half-life is defined as the time taken for half of the radioactive nuclei in a sample to decay. In other words, it's the time taken for the activity of a sample, measured in becquerel, to fall to half its original value. This time can be measured in seconds, hours, days, or thousands of years.
Some radioactive sources decay very quickly, with a half-life of only microseconds. Others have a very long half-life, running into millions of years.
Radioactive atoms decay, emitting radiation to form new atoms. The sample gradually becomes less radioactive. To investigate decay more closely, this is a sample of barium-137M. At time 0, the activity is 40 counts per second. After 2 minutes, it's dropped to 25. 4 minutes and the count rate is 15. After 6 minutes, it's about 7. The time taken for the activity of the sample to fall by half is known as its half-life. Plotting a graph of count rate against time produces a smooth curve. The activity falls to half its original value in just 2.5 minutes. It falls by half again 2.5 minutes later. So the half-life of barium-137M must be 2.5 minutes.
But each radioisotope has its own rate of decay. For example, iodine-131 has a half-life of only 8 days, while chlorine-36 has a half-life of 300,000 years. Suppose you had 32 grams of sodium-24, which has a half-life of 15 hours and decays into magnesium-24, a stable form of magnesium. An understanding of half-life and some simple math can help you determine how much of the original material exists after a given period of time. After 15 hours, half of the sodium-24 would have decayed into magnesium-24, leaving 16 grams of the original isotope. After 30 hours, there would only be 8 grams of sodium-24 left, and so on, until there's not enough sodium-24 left in the sample to detect its radioactivity.
Looking now at the uses of radioactivity, which are almost entirely based on the penetrating ability of the ionising radiation. First of all, smoke alarm. Alpha particles are easily stopped, and it's the stopping of the particles that sets off the alarm. Inside the smoke detector, there is a small capsule, and inside this capsule are metal plates, which provide a flow of electricity through the air. Now, air is normally a very good insulator. So how does this happen? The upper plate is connected to the positive side of the battery, and the lower plate connected to the negative side. At the base, there is a tiny disc of americium, which is an alpha emitter. These alpha particles only travel a very small distance, but in their travels they collide with the atoms in the air. An alpha particle striking an atom produces an electron and a positive ion. The electrons are then attracted to the positive upper plate and the positive ions to the negative lower plate. And this movement of electrons and ions is effectively an electric current. It completes the circuit. Whilst the circuit is complete and current flows, the alarm does not sound. The introduction of smoke disrupts not only the alpha particles, but also the flow of ions. As a result, there is no longer any current flowing, and this triggers a relay on the circuit board that sounds the alarm. So as soon as the current stops flowing, the alarm sounds. Gamma radiation will pass through packaging to kill bacteria, etc. It's used on things like rice and mangoes and spices to preserve them.
Using X-rays and gamma rays can also be used to treat food. By choosing the right wavelength and dosage, these rays can prevent sprouting of vegetables like potatoes, maintain their freshness and taste, and destroy harmful bacteria that could be present in spices, meat or seafood. Also can rid fresh fruits and vegetables of insects that might otherwise hitchhike, spreading to other regions of the world, where they could have devastating effects on the environment and agriculture. Food irradiation involves shining electromagnetic rays or beams of electrons onto food. The energy is transferred at an intensity necessary to give the desired effect. It is a cold process, so spices retain their unique flavors and aromas that would be diminished by heating. It also avoids reliance on chemical methods, such as fumigation or pesticides, to combat bacteria, insects or other spoilage organisms. In addition, those irradiation beams pass through packaging, so the food remains protected from bacteria or insects after treatment and will remain fresh.
Again, because of the high penetrating power, gamma radiation can be used to sterilize medical equipment, even razor blades in production. The gamma source used is something like cobalt rods, which are kept in water when not in use. Normally kept in a large water bath, the cobalt source is lifted out of the bath and pallets of packaged materials are passed around the source so that both sides are equally as irradiated. The gamma radiation emitted is sufficiently powerful to disrupt DNA within living cells, and by destroying the DNA, you kill the cell. Beta particles have a range of energies and therefore a range of penetrating powers, so can be used to gauge thickness and depth. This is a rolling mill for the production of steel, with a radioactive source, a beta source, above the steel sheet and a detector below. If the radioactive count goes up, the steel is too thin and the rollers are moved apart. If the radioactive count goes down, the steel is too thick and the rollers are squeezed closer together. This is a continuous monitoring process which is used for sheets of materials like steel, cling film or even toilet paper. The last area to look at is the diagnosis and treatment of cancer, and this is improving all the time. Starting with diagnosis.
Horse Polo has been showing signs of lameness, but an ordinary X-ray has not revealed any bone fracture. Polo is to be injected with a solution which contains a radioactive isotope called technetium-99. When a bone in the body is broken, even if only slightly, there is increased metabolic activity at the site of the problem. It helps to repair the damage. The solution injected into Polo also contains a substance which is transported around the body in the bloodstream. It acts as a carrier for the radioactive isotope. The presence of technetium-99 inside the body can be detected outside the body. When the detector is applied to various points on Polo's flank, a concentration of radiation is found in one particular area.
4,536.
That spot can then be more accurately looked at using a special scanner camera.
Each of these pictures is generated by a large number of gamma emissions from the horse, which are represented on the picture as a dot. And where the dots are most dense represents where there was the greatest radioactivity in the horse and hence the greatest uptake of our bone labelling substance. And you can see on the left leg, which you know is a sand leg on the horse, we can just see the outline of the skeleton showing that even normal bone takes up a small amount of the chemical. But on the right leg, where we know that there's a lame leg, there's a far greater number of dots representing a greater uptake of the chemical. And this place in particular, immediately below the knee, the carpus of the horse, we can see that there's an intense discharge of gamma.
An isotope such as technetium is combined with glucose and injected into the body. The solution passes throughout the body. It travels to every cell, but the concentration is greatest where the metabolic rate is highest. As a result, it will build up in areas where there is increased growth, such as where there's a tumour. The radioactive isotope is carried throughout the body by the blood, and when it gets to the tumour, it gives off a positive electron or a positron, which collides with an electron and they mutually annihilate, giving off 2 gamma rays. These gamma rays are detected outside the body and a 3D picture built by a computer. Isotopes used have short half-lives and need to be produced nearby. PET stands for positron emission tomography, positive electrons being given out and built into a picture. A radioactive isotope that emits positrons is attached to glucose and injected into the body. Positrons collide with electrons and they mutually annihilate, giving off 2 gamma rays which leave in opposite directions. The gamma rays are detected outside the body and a picture built by a computer. There are many ways that radioactivity is used to treat cancer.
New technology is making it modern and precise. It works by aiming intense bundles of energy at cancer cells, damaging their DNA. If a cancer cell can't repair its damaged DNA, it dies. But the radiation also damages nearby healthy cells. This is what causes side effects in neighbouring tissue. Most radiotherapy is given from outside the body, usually using X-rays, and new experimental techniques are improving accuracy. MRI scans could help track tumours that are difficult to pinpoint, such as lung cancers that move as we breathe. Experimental MRI-guided radiotherapy is being designed so it only fires the radiation when the tumour is in its crosshairs. IMRT shapes the radiation beam to match the tumour. This reduces the damage to surrounding healthy tissue. And a technique called SABRE uses more intense radiation beams. This gives a greater chance of killing the tumour cells and means patients need fewer hospital trips to finish their treatment. One problem with X-rays is they continue to travel through the body after they hit the tumour. This damages normal cells, but a different type of radiation given by proton beam therapy stops when it hits the tumour. This spares the tissue behind and helps treat tumours in sensitive locations. Radiotherapy that's given from inside the body can precisely kill cancer cells. Thyroid cancer can be treated with a radioactive iodine drink. The radioactive iodine is taken up by thyroid cells, but not others, and so has few side effects. Brachytherapy is a surgical technique where a radioactive implant is placed inside the tumour. The implants can be tiny metal pellets or wires, and they put the radiation exactly where it's needed. These different techniques help make radiotherapy more precise, minimizing the damage to healthy cells. And through research, this reduces side effects and could speed up recovery time.
There are 3 sources of nuclear energy: ionising radiation, a product of radioactive decay, basically what we've been looking at; nuclear fission, where energy is released by the splitting of a nucleus in atomic bombs and power stations; and nuclear fusion, where the energy is released when the hydrogen nuclei combine to make helium. This is the process that takes place in the Sun.
The power from the Sun comes from combining small atoms to produce larger ones. It's a nuclear reaction known as fusion. A minute fraction of the energy given off is beamed down to Earth, where it powers the wind, drives the water cycle, and gives the energy needed for life on Earth. Beneath the Earth's surface is a second form of nuclear energy. Large atoms decay by giving off alpha and beta particles, producing heat we can use for geothermal power. Fusion and decay are the two natural nuclear energies. A third form is fission. We'll look first at fission. The first use or misuse of fission was as a weapon. But unlike a bomb, the fission reaction in a power station is controlled so that energy is given off only on demand. Nuclear fission means the splitting of a nucleus into two smaller parts. The nucleus is made up of neutrons that are neutral and protons that are positive. If an extra neutron is added, the nucleus becomes unstable. As it wobbles and necks a little, the nuclear force gluing the nucleus is acting over a smaller area. It can no longer counteract the electrostatic repulsion of the protons. So, the nucleus splits in two, giving off 3 neutrons and energy. This is a chart of stable nuclei. Uranium has a very high proportion of neutrons to keep the nucleus together. When it fissions, the uranium nucleus can split into any one of 40 different pairs of nuclei. It takes 1 neutron to cause fission, but this fission reaction gives off energy and 3 more neutrons. If these neutrons hit other nuclei, they too will cause new fissions. This is a chain reaction. If it happens quickly and out of control, it's an atomic bomb.
This clip uses a whole series of mouse traps and ping-pong balls to demonstrate just how a chain reaction might occur. Don't forget, this is a slow-mo clip. It happens much, much faster.
After fission, a neutron is travelling very fast and will pass right through a nucleus. It will only be captured once it is travelling slow enough. If the pieces of uranium or plutonium are small, most of the neutrons will escape or be absorbed by the abundant U-238. If either of these happen, there will be no fission. As the pieces are brought together, more neutrons will be captured by U-235 nuclei, and this will cause fission. The smallest possible mass at which a chain reaction will occur is called its critical mass. This varies according to shape. For uranium-235, this is 15 kilograms. As it's dense, it would only be the size of a grapefruit. If the uranium is kept at the critical mass and the neutrons are controlled by absorbing the excess, power can be generated in components of a thermal fission reactor are a core of fuel, uranium, plutonium or thorium, moderators to slow down neutrons to the right speed, usually water but sometimes graphite, control rods to soak up extra neutrons, coolant, usually water but sometimes a gas, and radiation shields to protect people and equipment. In this reactor, water is being used as a moderator to slow down the neutrons so they can cause fission. The hydrogen in the water is similar in mass to the neutron, so a collision tends to transfer momentum to the hydrogen. However, the hydrogen in the water will absorb neutrons to become deuterium. If heavy water is used, that is water made with deuterium, uranium can be used without enrichment because no neutrons are lost. As the neutrons slow down in the water, they heat it and boil it off. The fission reaction is controlled by controlling the number of neutrons. Boron or cadmium control rods capture neutrons depending on how far they're inserted. At the first sign of any emergency, control rods are immediately put in place. In the case of a boiling water reactor, the moderator is water, which is allowed to boil off as steam, which drives the turbines.
So, the key points of nuclear fission. A slow-moving neutron is absorbed by the U-235 nucleus. The nucleus becomes unstable and splits into two daughter products. This releases two or more fast neutrons and a large amount of energy. Fast neutrons are slowed down by moderators, and this allows them to continue in a chain reaction. As just said, moderators slow down the fast neutrons so that they can be captured by more U-235 nuclei, resulting in a chain reaction. Control rods capture the neutrons completely, limiting the chain reaction. And then, of course, the fuel rods are made from the U-235, which is an isotope of uranium.
This graph shows the binding energy per nucleon for different nuclei. That is the energy that would be released if the nuclei was made from the beginning by adding protons and neutrons together. Hydrogen obviously has zero binding energy. If the proton and neutron of deuterium was added to another deuterium nucleus to make helium, a huge amount of energy would be released. Less energy would be produced in splitting uranium to, say, strontium or barium. The energies involved are millions of times greater than for chemical energy. To release energy, you have to work towards the maximum, somewhere around iron. This giant machine is designed to heat and hold a very high temperature gas in imitation of the sun's processes. In a fusion reaction, energy is released when light atoms are fused together. The great lure of power from fusion is that the basic fuel is deuterium, a form of hydrogen. Deuterium can be extracted from water. It is virtually inexhaustible. This is the smallest atom, hydrogen. Its nucleus is one proton, which is positively charged. It has one electron. However, the electrons don't play a direct role in nuclear reactions. This is an atom of deuterium, an isotope of hydrogen with a neutron in the nucleus. Deuterium occurs naturally in water and can be separated by hydrolysis. Being twice the mass of hydrogen, it does not reach the electrodes as quickly, so is left behind. Tritium is another isotope of hydrogen with two neutrons and one proton. Being extremely rare in nature, it would have to be made from neutron bombardment of lithium or separated from heavy water in a heavy water cooled reactor. The likeliest way to fusion power is to use the nuclei of these two atoms, but each nucleus has a positive electrical charge, so when they come close together, they repel each other. The only way to force them together is to make them collide at thousands of kilometers per second. To do this, they are heated to enormous temperatures, greater than 100 million degrees Celsius, 6 or 7 times hotter than the center of the sun. Well below that temperature, the particles are stripped of their electrons, which race around independently. This mixture of positive and negative particles is called a plasma. Some of the nuclei will collide and fuse together, forming a new single nucleus while ejecting a neutron. But how can this super-hot plasma be held together so the collisions can happen? If the plasma hits the walls of a container, it cools instantly. This loss of energy prevents fusion reactions happening. Magnetism can be used to hold the plasma because charged particles can be trapped in a magnetic field. Particles travel around the lines of the magnetic force, so they're prevented from moving rapidly towards the walls. To stop the plasma escaping from the ends of the container, it is bent back on itself in a donut shape called a torus. The plasma is trapped in a ring with no ends from which to escape. The magnetic field confining the plasma inside the torus is produced by a series of coils around the torus. One of the main challenges so far has been to mould the magnetic field to the most optimum shape. In a commercial reactor, the plasma will be wrapped in a blanket containing lithium, which absorbs the neutrons. Most of the energy being released from fusion reactions will be released as high-speed neutrons flying out of the plasma. These neutrons, travelling at thousands of kilometres a second, are slowed down by colliding with the lithium. The slowed down neutrons react with lithium to produce tritium and helium. The tritium can then be used to fuel the reaction. The fuels for fusion will be deuterium and lithium. In slowing down the neutrons, the lithium becomes hot and will boil water to produce steam for power generation.
Hydrogen and deuterium nuclei are turned into a plasma at very high temperatures. Millions of degrees are required to provide the kinetic energy or the speeds sufficient to overcome the electrostatic repulsion of the protons. Very high pressure is needed to increase the chances of a successful collision. And then the byproduct is helium and fast neutrons which collide with the lithium walls, producing heat.
Waste is classified into levels. In the UK, there are 3 levels: high, intermediate and low-level waste. In the USA, there is no intermediate classification. High-level waste is sometimes mixed with molten glass and stored on site until it cools down. While they cool, they are stored in concrete vaults. The concrete is sometimes filled with iron shot, which is twice as dense as concrete. Much work is going on to test the disposal of high-level waste in deep underground stable rock formations. The radiation from the fuel rods won't be safe for nearby humans for 500 years. After that, it would be harmful if swallowed for 1,000 years. Canadian researchers are testing granite 500 to 1,000 metres underground. They're finding out if underground water will become contaminated and checking the long-term effect of heat on the rock. The most acceptable method of disposal for the future seems to be underground in stable rock formations. In the UK, intermediate level waste includes the cladding stripped off the outside of the fuel rods. Usually it is encapsulated in concrete inside stainless steel containers. These too await permanent storage. The world's first deep underground repository is at Forsmark in Sweden, under the sea. It's used for low-level and intermediate waste. Containers of waste are placed in position with this remotely controlled truck. When the containers are packed in, the vaults will be filled with concrete and a thick cap of concrete will cover the top. The internationally accepted safest method of disposal is underground in stable rock with many different barriers to prevent water flow carrying away pollutants. The challenge is to find areas with extremely slow water movement. The Forsmark repository is under the sea. Low-level waste includes clothes and instruments that might have picked up some contamination. It is placed into drums or containers and disposed of in concrete-lined cells and covered over with earth and then replanted. Nuclear power costs about the same as other forms of fuel. It has the advantage of not releasing carbon dioxide or smog-producing chemicals. However, some poorly managed power stations have caused radioactive contamination and unease about nuclear power. Commercial fusion power is unlikely before the year 2040. Current thinking is that it's far better to save energy than build new power stations. Nuclear power is only one of many energy options. We must look for ways to reduce our need for power and work out the most environmentally responsible methods of generating power.
And that's it. Thank you for watching.